Next, I'd like to talk about Shor's factoring algorithm. And I'd like to begin with the dream of every cryptanalyst. Here's a code breaker, and he has a dream. He's going to crack RSA crypto systems by finding a super fast factoring algorithm. And of course, if he could do that, he would be rich and famous. Here's the problem. Given an integer n, what is the product of two unknown primes, p and q, where n equals pq? Find p and q, that is, the factors of n, or factor the integer n. Here's a simplified Shor's algorithm. Step 1, we choose an integer a such that it's relatively prime to the integer n. How do we do that? We simply guess. If n is a very large integer, then it's very unlikely that a would not be relatively prime to n. If a is not relatively prime with n, then we've essentially factored in. There's no problem. Of course, the probability of being so lucky is astronomically small for a very large n. Step 2, we use a quantum computer to determine the period p of the function a to the x mod n, where a is an integer. Step 3, p is not even, then we simply repeat the process. Go back to step 1 and start over again. Eventually, we'll find an example where p is even. Step 4, if p is even, then a to the p minus 1 can be factored, mod n, into two polynomials in a. This is high school algebra. And so the Euclidean algorithm can be used to compute the GCD of these two factors. If the above GCDs are p and q or q and p, then we factor it in. If not, we'll just go back to step 1 and repeat it again. So let's take a look at the full algorithm. Step 1, step 2, step 3, step 4. There's nothing new about this algorithm except what Shor has done is taken an old classical algorithm and replaced step 2 with a quantum algorithm. That is, use a quantum computer to determine the period p of the function. And so let's take a closer look at the quantum part of the algorithm itself. Let's take this. Blackboard z is to represent the integers 0, plus or minus 1, plus or minus 2, and so forth. Problem. Given a periodic function from the integers to the integers, find the period p. Unfortunately, it's exceedingly difficult to put an infinite number of integers on a computer, so we have to do something. We have to make an approximation. What we'll do is we'll choose a sufficiently large positive integer q and restrict f to the set of integers from 0 to q minus 1, and focus on the function restricted to that particular set. We now have a function that can be placed on a real computer. How do we choose q? Well, q is somewhere between, is a power of 2 that's between n squared and 2n squared. Simplification. To avoid minor technicalities, we assume that q is a multiple of q. We don't really need to make this assumption, but if we don't make the assumption, then we'll end up working with partial sums and tails of sums, and the combinatorics is straightforward but tedious. We will avoid that, but we're losing no essential part of the algorithm. Okay.
You said Q is a multiple of Q.
P is a multiple of Q. I'm sorry, I should go back then. I said it wrong. Let me go back. Okay. So let's take a look at that. Let Z be the blackboard Z be the set of integers. Problem: given a periodic function f, from the integers into the integers, find the period of P. What we'll do, we wish to place this on a computer. This is a function over an infinite domain, so we need to restrict the domain Z. So we will choose a sufficiently large positive integer q and restrict f to the set of integers from 0 to q minus 1 and focus on the restricted function. In so doing, the period we find will be an approximate period. We'll talk about that later. To avoid minor technicalities, we assume Q is a multiple of P, that is, P divides Q. We don't have to. The same arguments work, but by making this technical assumption, we avoid spending a lot of time working with small pieces or tails of sums. Nothing essentially is lost by so doing. Shor's algorithm continued. Let's choose an integer n such that q is less than 2 to the n, and the maximum value of f is less than 2 to the n. A better way of doing that is to choose q between cap n squared and 2 times cap n squared. Construct two n-qubit registers, register 1, register 2, left register, right register, and each contains n bits. I've denoted the bits in the first by the A's and the bits in the second by the B's. The first register is constructed to hold the arguments of the function f. The second register is constructed to hold the values of the function f. This is standard procedure in representing functions in quantum computing. As convention, essentially bits in the states ket n-1, tensor ket n-2, and etc. represents the binary expansion of an integer. That's our way of representing integers. As an example, we represent the integer 23 as the tensor product of ket 1 with ket 0, tensored with ket 1, and so forth. Now we'll apply the Q-point Fourier transform. Let omega be a primitive qth root of unity, which is the exponential of 2 pi I divided by our integer q. And of course, we have the set S of q of integers from 0 to q minus 1. And the Fourier transform is a transformation which takes a function from our set SQ to the complex numbers into another function, the Fourier transform function, from SQ into C, and is simply defined by this expression. You can see that the matrix omega to the xy, where x and y range over the integers, is the Fourier transform matrix. We will implement our Fourier transform as a unitary transformation, and luckily the Fourier transform is unitary. In fact, quantum mechanics depends on that fact. Shor's algorithm continued. Step 2. Now we'll go into details of the quantum part of the algorithm. The first thing we do is we initiate both n-bit qubit registers to 0. The next step is to apply the Fourier transform to the first register, to produce the expression shown. The next step, hence, register 1 now holds in superposition all the integers from 0 to q minus 1, where actually q is a power of 2. And the next thing we do, step 2, is apply a unitary transformation, u sub f. F is the periodic function, which takes f each of the 2 to the n possible integers into the corresponding value. So now we have, after this operation, we have in superposition all argument function value pairs for the function f. It's an amazing amount of superposition. It'd be nice if we could use it immediately, but we can't. If we were to look at our registers after this operation, the system would collapse to simply one argument function value pair. Before we do anything more, let's just apply a little algebra. What we're going to do is split this sum up into 2 parts. It's very technical. You can imagine what it would be like if we didn't assume that p divided q. Details of this are worked out for p not equal to q in one of my papers. Essentially reduces to an expression of this form. This is essentially what's stored in the register. And we thus have that the expression for the registers is given by the expression on the right. We sum over J0 and then sum over J1, over the integers pJ1 plus J0. If we look at the right register, we don't really have to, but it makes it easier to explain the algorithm. Immediately, the system chooses one of the integers j sub 0, which we'll call r sub 0, and becomes the state so indicated at the bottom. Another way of doing this is simply to ignore the right register. It's no longer used. R0 is some integer, we don't know what it is, from 0 to p minus 1. If we're to measure this now, we wouldn't get any information, so we have to be a little more subtle. The next thing we do is to apply the Fourier transform again to register 1. And let's do that. Step 2.4. Applying the Fourier transform, you can see that you have an expression that can be reduced to the expression shown at the bottom of the page. Let's take a closer look at that. Inside the summation is another summation which can be greatly simplified. That expression is either q divided by p if y is equal to 0 mod q over p and is 0 otherwise. Hence, the whole expression for the registers can be simplified to the following. Now what we have in our left register is essentially a multiple of a rational number of the form q over p. And now what we'll do, finally, we measure the left register, and we end up with a multiple, a random multiple of q divided by p for some lambda 0. Now, what we do at this step is repeat the algorithm 1 through 5 until we have enough multiples, q over p, to recover q divided by p. I'd like to make a remark here. I'd like to remind everyone that the above description is a simplification of Shor's algorithm, although it has the essential features, which contains most of the key features of the actual algorithm. A more detailed and thorough explanation can be found in many papers, and I list some of them here. In Shor's actual algorithm, he uses the continued fraction expansion to find the period. The algorithm actually produces an approximate period, and the continued fraction expansion is used to find the very close but different true period. And that is essentially it. Thank you very much.